Okay, so now we're going to talk about planes in three-dimensional space. And I'm going to define the plane in three-dimensional space very much like we just defined the line in three-dimensional space, using a point and then a direction vector, sort of. It's actually what's called a normal vector, which for those of you not in physics, normal just means perpendicular. So it's a vector that's actually, if you imagine your plane, then it's a vector sticking up, or one of the directions, perpendicular out of the plane. And so let's see here. When we first start doing this, I think you'll notice something pretty cool about this, and maybe you can even imagine where we're headed. All right, so I'm going to draw my plane here, and there's my plane. It's in three-dimensional space. It's oriented some way, shape. I don't know. And what I'm going to describe is there's going to be a point in the plane. Call it point P, whatever. And it's got coordinates x1, y1, and z1. And then the way this works is we imagine a normal vector perpendicular to our plane. Now let's see, does that? Yeah, that looks perpendicular. So this normal vector, I'm going to call it n vector, very creatively named, I know, is some, ai b times j c times k vector, or you can write it the other way, a, b, c, like this, however you want to write it. Then the vector equation for our plane can be written like so. A times x minus x1. I'm sorry, I said vector, I meant standard form, sorry. Y minus y1. C times z minus z1. And that all is going to be equal to 0. If you've done some work in three-dimensional before, you probably learned somewhere along the way they said, oh, the equation of a plane is always going to be ax plus by plus c times z plus, oh, oops, I went off the page. Come back. Plus d equals 0. And guys, that's just distributing the coefficients into this and then combining all the constants. A times x minus a times x1, that's going to be some kind of constant because x1 is a coordinate. We know x is the variable. B times y plus negative b y1, another constant. C times z minus cz1, another constant. You just combine those three constants into what we call d in the other one, and you get the same thing. So that's pretty much exactly how we're going to write the equation of a plane in three space. Now, where the real work comes in is this normal vector, because a lot of times, we want to come up with the equation for our plane. We're given information about the plane, not about some vector that just appears and it happens to be perpendicular to the plane. And if you're thinking about what we did last week, you are correct. How could we possibly come up with a normal vector, a vector perpendicular to a plane? Well, obviously, we know how to come up with a vector perpendicular to two vectors. So back in geometry, you probably learned something like this, that 2 points determine a line, 3 points will determine a plane. Well, let's see. If I give you 3 points, 2, 1, 1, 0, 4, and 1, and negative 2, 1, and 4, there's our 3 points. That must determine a plane. And if it determines a plane, we can come up with the equation for said plane. So let's see. We would probably want to turn these into 2 vectors, which of course we can do. We can take, I'm going to call one vector u vector, and I'm simply going to take the vector from 2, 1, 1 to 0, 4, 1. And notice that creates the u vector, -2, 3, 0. And then I need another vector. How about v vector? And what's v vector? You're like, well, I want to use the same point. I still want to use 2, 1, 1. It's just now I want to find the vector from 2, 1, 1 to the other vector, -2, 1, 4. So we have -2 minus 2. We have 1 minus 1. And we have 4 minus 1. And so v vector is -4, 0, and 3. So now I have these 2 vectors that are somewhere in 3 space, but because they are these 3 points, we use the same point, the 2, 1, 1, to create these 2 vectors. The 3 points are coplanar, so the 2 vectors are in the same plane. So using cross product, we can come up with a vector perpendicular to both of these vectors. Well, if it's perpendicular to both these vectors, guess what? It's perpendicular to the plane that contains them. And so to come up with the normal vector, all we're going to do is cross u vector and v vector. Now, last week, we talked a lot about how to do that. So this is where a cross product comes in handy. Let's see, u vector goes first. Only because that's the way I wrote it. I wrote u cross v. So if you want to cross v with u, go right ahead. Your vector will be perpendicular. It'll just be pointing the other direction from the one that I'm going to come up with. I can't remember what we did last time, guys, if we did diagonals or minors. I think it was minors. So even though it's not my preferred method, I am going to use the diagonals method because I know that some of you prefer that method. And so let's go ahead and set up our diagonals method here. I don't like that purple color. It doesn't seem to show up as well, at least on my screen. So notice I have I times 3 times 3. 9 i's. I have j times 0 times 4. 0 j's. K times -2 times 0. So we didn't get any j's or k's going that direction. Let's go the other direction. Now these are minuses, right? So minus -4 times 3 times k. That's -12k. And let's go 0 times 0 times I. 0 i's. And look, 3 times -2 times j. So minus -6j. And the result is a vector that is 9 i's, 6 j's, and 12 k's. And that's our normal vector. So now, using our normal vector right here, and any point that we have in the plane, it doesn't matter. These are all in the plane. But since when you do the cross product, just visually draw one out one more time. If I cross product this vector, oops, I didn't mean to do that. I want to go the other direction. There we go. And this vector, remembering that the cross product is perpendicular at the point where the two vectors meet down here at the tails. And that's the point 2, 1, 1. I'm going to go ahead and just use 2, 1, 1, since that's the point that's common and that's where the vector goes up. And so I can see that the equation for my plane then would be, can I scroll this? Make more room? No, I can't. All right, well, I'm right at the bottom here. 9 x minus x1, which is 2, 6 y minus y1, which is 1, and 12 z minus z1, which is also 1, equals 0. And we'll just distribute them out, I guess. 9x, 6y, 12z. And notice we have a negative 18 from the x. We have a minus 6 from the y and a minus 12 from the z. You know, this is a negative 36. These are all, you know, 9x plus 6y plus 12z minus 36. And, you know, look, they're all divisible by 3, right? So divide by 3 just to get it in the simpler terms. There we go. And that's our plane equation. So that's what a plane in three-dimensional space can look like. And that's pretty much it for today's work in lines and planes. For Thursday, we will be looking at distances in three space, distances between planes and points and lines and points, and finding lines that are in planes, and sort of some other applications of lines in planes in three space. So with that, I'm going to tell you all good luck. Hopefully this video helps, and I will launch or send out another video on Thursday. Probably just one, because it shouldn't take too long. All right. Have a great day, everybody.